So what is the quorum condition and how does it help to achieve consistency in a replicated peer-to-peer database? So hello guys and welcome to another Dev Coffee Talk. So in today's Dev Coffee Talk I have a very interesting topic, which is the quorum condition or the quorum technique in peer-to-peer replicated databases. So this is a very powerful and very well-known technique in this type of distributed DB architectures. So if you ever face this type of architectures, this will be very useful for you to stand out as a software engineer. Let's get started. So we are basically working on a software as a service or an enterprise application, and as the company grows, there will be more and more clients that will need to process their data. So for that, we have decided to implement replication in our database. So this is a very popular and powerful technique to increase the throughput and provide fault tolerance and of course help with latency issues. So by using replication in our databases, we can mitigate single points of failures by having replicas that can serve read and write operations, especially read operations. We can increase the throughput as now we'll have more machines, more DB instances that can help to deal with the increasing number of writes and reads. And we can reduce the latency by placing some of these replicas close to the users. There are mainly two types of replication. We have leader-based replication and leaderless replication. So in a leader-based replication, we are talking about a master-slave variation. So a node will acquire the role of a leader and will be the only one that can process writes, whereas the others will be the followers. So the leader node will periodically send updates to the followers to keep their local copies of the data in sync. We'll leave leader-based replication for another video. If you are interested in this topic, just let me know in the comments. And today we'll talk about leaderless replication, also known as peer-to-peer replication. So in peer-to-peer replication, we don't have different roles. So each node is essentially a peer to the others. That means that any node can actually handle any type of operation, either write and read operations. We could literally read data from one node and write data to another one. These nodes will talk to each other periodically to send their updates so as to ensure that all of them will see the very same snapshot of the data. That is consistency. Of course, this is a very interesting challenge that distributed architectures have to cope with. We know that the network cannot be trusted, mostly because of anomalies and errors. So knowing that the network cannot be trusted and that consistency is eventual, how can we ensure that any write operations we perform on these type of databases will actually be there later on whenever we read? Well, let me introduce you to the quorum technique. So this is a very powerful algorithm used in peer-to-peer replication. It's basically a voting algorithm and it works like this. Let's say that we have n nodes in our cluster. That is n machines running each one its own copy of the database, its own replica. Every time we need to write to the database, we need to make an update to our data, we wait for W nodes to confirm the operation. That is, we as a client connect to N nodes, or W at least, and we wait for the confirmation for a write operation from W nodes. W is a number. Later on, if we ever want to read from our database, we will need to fetch the data from R nodes out of the N. R is another number. Here the quorum condition states that W plus R should be greater than N. What does it mean? Well, let's break it down with an example. Let's say we have N equals 3. That is, we have 3 nodes in our cluster, in our peer-to-peer replicated cluster. Let's say we pick W equals 2 and R equals 2. That meets the quorum condition, right? Because 2 plus 2 is greater than 3. Now, what does it mean? Well, essentially, if we ever write to the database, to the cluster, we will need 2 nodes at least to confirm the operation. That is, our update should go to at least 2 out of the 3 nodes. Later on, whenever we read from the cluster, we will need to pick at least 2 nodes to fetch the data from. So as you can see here, the quorum condition ensures that at least one of the nodes overlaps within the W and R groups. That is, at least one of the nodes we are reading from has the data we just wrote to the DB. So we can assume that each data item has a version number attached to it. If one of the nodes goes down for some time because it has some errors or because it's going into maintenance mode or something like that, then the 2 other nodes will be available for us. We write to the database, so we connect to these 2 nodes because W equals 2, so the 2 nodes will confirm the operation and the version number for the data item will be updated. Now, if we ever want to read the same data item from the cluster, we will need to pick 2 nodes. Let's say the failing node is up and running again, but it doesn't have the updated version of the data. Any combinations of 2 nodes that we can make out of the 3, we know that at least one of them will have the updated version of the data item. And this is a magic behind the quorum condition. Now, what happens if the quorum condition is broken? Let's say we pick R equals 1, keeping W equals 2. Now, in this scenario, 2 out of the 3 nodes will be always up to date because we are writing to 2 nodes out of the 3. Now, by picking R equals 1, we cannot ensure that the node we are reading from will have the updated data because we can actually pick the stale node. And that is because we are not following the quorum condition. Now, let's do the opposite. Let's keep R equals 2 and W equals 1. In this scenario, only 1 node out of the 3 will always be up to date. But 2 out of the 3 nodes in the cluster might be stale and never get the updated item. So as we picked R equals 2 and we are not meeting the quorum condition, it could be that we might read from the 2 outdated nodes if we are unlucky enough, hence not having the fresh version of the data. So in these 2 scenarios, we can see what happens if the quorum condition is not met. Essentially, what happens is that the group of nodes that processes our writes is not overlapping with the group of nodes that is processing the reads. So we might be reading and writing from 2 different nodes and the data item is only in one of them. If the W and R groups are not overlapping, then there is no way we can ensure data consistency across the cluster. And that is all for today's, guys. It's a very quick video and I wanted to show you how the quorum condition works. So if you like this video and found it interesting, please hit the like button and subscribe for more content like this. Let's keep learning together. Bye bye.